All right. Good morning, afternoon, or evening, everybody. Welcome to the Discover and Access the OPERA Surface Displacement Dataset using ASF DAAC's Displacement Portal. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Saving Time, so we are going to go ahead and get started. What I'll do first today is begin with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any questions or you have any issues, please enter them into the Q&A panel rather than the chat, and you should see that on the right side of your screen. If you don't see the Q&A panel, click on the three dots at the bottom of your screen, and that will pull up your panel options. You can then add the Q&A panel by inserting a check mark next to it. A quick word about the chat. Participants will have the capability to chat with the hosts and presenters, but not all other participants. So if you have any questions, please enter them into the Q&A panel, again on the right side of your screen, rather than the chat. Today's webinar is being recorded. Once completed, I will send an email to all registrants and participants that includes links to both the recording and presentation slide deck used within today's webinar. As far as timing is concerned, today's event will be 1 hour long with 45 minutes allocated to the presentation and live demonstration and an additional 15-minute question and answer period to begin after the presentation. Depending on the volume of questions that we receive, we may extend the Q&A session, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During today's webinar event, and let me actually advance the slide here. All right, during today's webinar event, our speaker is Forrest Williams. Forrest will kick off this afternoon's webinar event with an overview of the NASA JPL Observational Products for End Users from Remote Sensing Analysis, or OPERA, Surface Displacement Dataset, and it will be referred to as the OPERA-DISP Dataset throughout the presentation. From there, he will cover the caveats for using the data and will end his presentation with a live demonstration that shows participants how to use the ASF, or Alaska Satellite Facility, Displacement Portal for working with OPERA-DISP datasets. During this afternoon's Q&A session, we will have two Q&A panelists, also from the Alaska Satellite Facility and NASA ASF DAAC. We have Kathleen Christensen, a product owner at ASF DAAC, and Gregory Short, a search and discovery subject matter expert at both the Alaska Satellite Facility and NASA's ASF DAAC. Before I toss it over to Forrest, I wanted to cover one final note about the Q&A session. We will try to answer all questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. With that, it is my pleasure to introduce today's speaker, Forrest Williams. Forrest, and with that, Forrest, let me stop sharing my screen and toss it over to you.
Awesome. Well, welcome everybody. We're really excited to talk about these new products and the tools we've built on top of them with you all. Like was said in the intro, my name is Forrest Williams. I'm a research software engineer at the Alaska Satellite Facility. I've used a lot of time series InSAR data within my own work, which is what we're going to be discussing here today. And we're really excited to bring this to you from ASF. You know, we spend a lot of our time thinking about how we can make SAR data easier for everybody to use. And we think this these new products and the displacement portal we built on top of them is going to go a long way to making SAR easier for everybody to use. So just going over the agenda quick. From my perspective, I'm going to give you all a brief overview of what exactly these OPERA-DISP products are. And then we'll go into some important caveats for how to use these products. And then we'll spend a lot of our time actually demoing the new ASF Displacement Portal. And then we'll leave a very healthy amount of time to do some Q&A, because I imagine there'll be lots of questions about all these new capabilities we're going to be discussing. So starting off, what are these OPERA displacement products? And the key thing to take away here is that the OPERA-DISP products are measurements of surface displacement of the Earth's surface at centimeter scales. They're really useful in a variety of contexts, but particularly useful for studying displacement from earthquakes, groundwater withdrawal, landslides, building instability, and many other things like that. The algorithm was fully developed, and the products were created by the JPL Opera team at the behest of the Satellite Needs Working Group. And we here at the Alaska Satellite Facilities are hosting these products and making them available for download and exploration through our Vertex website and through the new ASF Displacement Portal. And in terms of what the type of analysis actually contained within these products is, these products are a PS plus DS time series InSAR dataset. Now, don't worry if several of those words in that statement didn't make a lot of sense to you. What we're going to be going over in the next set of slides is what exactly it means for something to be a PS plus DS time series InSAR dataset. So let's start with what is InSAR. This is a technique you might be familiar with if you've worked with synthetic aperture radar data in the past. But to really talk about InSAR, we got to talk a little bit about what exactly a synthetic aperture radar satellite is. And what's important about a SAR satellite in this context is that it is an active type of satellite remote sensing data set that emits signals in the radio to microwave spectrum. And the fact that we're sending our own pulse of light and that we can of microwave radiation and that we can measure the return very exquisitely is what gives SAR a lot of its interesting properties. And one thing that makes it very interesting in particular, which is that while like typical satellites, we measure the strength of the signal that is returned when we send out a pulse, and that's the amplitude component of the signal. SAR satellites also measure the phase that is being returned. And the phase is essentially where in a wave cycle from peak to trough, typically measured in units of 0 to 2 pi, where in that peak to trough cycle, the signal is when it's returned. And this is really key because this tells us a little bit about how far it is from the satellite to an object it's trying to measure. And how this process typically goes is that we have a satellite fly over a particular location and take an image where it measures both the phase and the amplitude component. And then several days later, when we might expect some motion to occur on the Earth's surface, say from landsliding or groundwater withdrawal, we take another image and once again, we measure the phase and the amplitude. Now, if the ground has moved away from the satellite slightly, let's say because the landslide has moved down, that will actually cause the path that our signal has to take from the satellite to the ground and back to be ever so slightly longer. And because that path is slightly longer, that also means that the phase of the wave that we're going to measure upon its return will be slightly different. And by subtracting the phase at each individual pixel within the two images that we took, we can actually get a measurement of how the phase has changed in between the two places and therefore get to some measure of the displacement that has occurred between the two time periods where we took our images. And this is the process that we call InSAR, or interferometric synthetic aperture radar. And it's a really key data set that we provide a lot of options to work with here at ASF. And it's also the basis of how these OPERA displacement products are created. So that's InSAR. And now the next portion of what the OPERA displacement products are is they are a time series InSAR product. And so what a time series InSAR product is when you combine many InSAR images together to reconstruct a displacement time series that measures displacement over a longer period of time. So a couple of reasons why this is important is one, since InSAR data are sensitive to measurements on the millimeter to centimeter scale, you can imagine there are a lot of things that could cause millimeter to centimeter level noise in the data set. And so a couple common sources of this are some change in the amount of time it takes the signal to go from the satellite down to the ground and back because of changes in the atmosphere. You also just have random noise in your analysis. And then you also have the random variations on the Earth's surface, say from shrink swell of soil or changing vegetation or things like that. And so we use time series InSAR both to try and isolate the true signals that we're actually concerned about finding inside these InSAR data sets, and then also to construct measurements of InSAR data for many different time periods. As I mentioned earlier, InSAR is always a measurement between one date and another date. And sometimes you want to know how the displacement is changing over a long time series. And by stacking up different InSAR measurements of the same location, we can actually begin to construct a full time series of how deformation has occurred at a given location. And this is really important because a lot of different displacement types have some sort of time dependent component. You could imagine that an agricultural growth and fallow cycle might affect how much groundwater is being withdrawn at a given point and would change how the displacement is occurring. And similar things can happen with landslides. Landslides tend to move faster under wetter regimes, and so you might expect to speed up when there's wetter conditions and slow downs when things get a bit drier. And by using time series InSAR, we can start to look at those temporal patterns and how the displacement is occurring. So time series InSAR is kind of a big umbrella term. And then when we drill down into the specifics of the InSAR data, there's two key ways that we can actually perform time series InSAR analyses. And they really both depend on the type of terrain we're looking at. So the first technique I want to talk about is persistent scatter or time series InSAR. And this is a type of time series InSAR that's particularly applicable when you get very, very strong returns of very stable features. And in particular, imagine that you're trying to do a time series InSAR analysis for a building or a barren rock outcrop that we would expect to have a very, very, very strong signal in the radar return, and also to not have very much random motion that would cause it to kind of have jitter over time in the InSAR analysis. And what we can do with these types of scatterers, these very stable, very strong return scatterers, is that we can treat them as essentially single points in our analysis. We can look at a particular pixel where this type of scatterer or feature occurs and just do a single pixel time series analysis for that feature. And the great thing about this is that it's the highest resolution we can get. You know, we're working at very close to the native resolution of the SAR imagery that we have. However, there is a big caveat here, which is that unfortunately the world is not made up of only persistent scatterers. There are a lot of different other scatterers, like you know, imagine agricultural fields or grasslands or other things like that, that don't have this persistent scatterer quality. They don't have that strong of a return. And so if we looked at only the persistent scatterers, we would actually have pretty low amount of spatial coverage. You know, we would have a lot of areas in the data set where we actually couldn't retrieve a measurement because we don't have one of these scatterers that we're looking for. However, kind of paired with there's another technique to try and work with these scatterers that don't have quite as strong of a return signal. And these scatterers are called distributed scatterers. And a good example of this would be something like a grassland or a farm field, or maybe a landslide that has the vegetated surface, but not one that has like trees and other things on top of it. And the idea here is that we treat less coherent, but features that tend to behave like each other and occur over a relatively large area. We try to treat those as one scatterer by basically averaging them all together. So you could imagine averaging an entire farm field together or something on that scale. And you know, a drawback here is that they are lower resolution because we are doing this averaging. But by averaging all of these points together, we can also really improve the overall data quality, the signal noise ratio, and we can actually start to treat, we can actually start to look at how the InSAR is behaving over time, because you know we have enough information here that we can actually start to do that. And the nice thing about distributed scatterers is there are typically much more of them in the landscape than persistent scatterers, just because you know the thresholds or the limits we have on how high quality the data needs to be before we can use it are much lower. And so this is really great. You know, we have a technique for measuring very precise measurements for very high quality scatterers, but then also a technique that we can use for lower quality scatterers that, you know, we sacrifice a little bit of resolution, but we can still get the coverage that we're looking for. Now, you might kind of be thinking, okay, these techniques seem pretty complementary. It might make sense to put them together. And that's exactly what PS plus DS time series InSAR is. It's basically the idea of like, okay, let's do a first analysis to understand where in our InSAR data do we have these point scatterers that are very, very reliable and we can treat as single points. Let's treat those as single points and not doing averaging in those locations. But then for areas that don't have this characteristic of being a persistent scatterer, let's do some more averaging so that we can get some InSAR measurements in these locations as well. And then by pairing these two together, we can kind of get the best of both worlds, where we're getting the highest resolution possible in areas where we have really high quality data, but we're not also sacrificing a bunch of spatial coverage because we're only focusing on these very high quality locations. And this is fundamentally the technique that the OPERA displacement products are using under the hood. They are PSDS time series InSAR technique using some of the latest methods. And if you're curious about more of the details here, I'm happy to go into that in the Q&A section of this talk. So now we've covered a little bit of what the algorithm behind the scenes for creating these products is. Let's talk a little bit about the overall specification of this project. And the first thing to mention is just the spatial coverage. Like, where is the OPERA team going to be producing these products for? And the answer there is most of North America and the US's outlying territories. This extends all the way up to Alaska and a large portion of Canada, although some of the northern regions of Canada are covered, and then we'll extend down into Mexico and Central America as well as many of the US's outlying islands, kind of in the Pacific and everything like that. Right now, the temporal coverage of the data is from 2016 to the end of 2024. This is in particular just for the time period we're in now, where the OPERA team is back populating the data set for all locations that it's going to cover. And because they're doing the analysis from 2016 to 2024 for the entire coverage area right now, that's taking a little bit of time. And so basically they're going to go through the effort of back populating the data everywhere up to 2024, and then they're going to turn on forward processing at the end of the year, where they'll start to populate the data for 2025 onwards. And then from that point on, as long as the Sentinel-1 mission is running, which is the actual data set that is being under the actual SAR mission that's being used under the hood to create this data set, as long as that's still flying, I believe they have plans to keep creating this data set for the Sentinel-1 data record. And then in terms of pixel spacing, the data is posted at 30 meters, but once again, kind of depending on how much persistent scatterers versus distributed scatterers there are in your scene, you might see the spatial pattern be a little fuzzier or a little sharper. So that's some of the basics. And now let's talk about the actual files that the OPERA displacement products are made out of. So very similar to what NISAR is going to be producing, these are cloud optimized NetCDF files, and you can download these files directly from our search website, Vertex right now. And while there are many layers in these products, and unfortunately I don't have time to cover all of the useful things and the useful layers inside of them, I'll just mention 4 of the big ones. The first is you have the main displacement data set, and this is kind of the key one that actually records the PS plus DS time series InSAR analysis that I've been talking about today. And in this data set, you'll see the displacement signature from both long wavelength signals like plate motion or things like that, and some of the smaller signals as well, but sometimes they can be swamped out by other impacts. And that kind of brings us to the second layer on them in these products, which is a filtered local displacement data set. Now, this is really key because we know that a lot of people who want to use the OPERA displacement data set want to use it to identify local sources of deformation like groundwater withdrawal or unstable slopes or landslide behavior. And sometimes this signal can be swapped out by noise or other larger displacement signals when you look at the standard displacement data. And so this filtered local displacement data provides a way for people to look at the displacement that is very localized. And this is really nice for finding those smaller grain features. The third data set that's always good to keep in mind is there is a coherence data set in each of these products. And this basically, for those of you unfamiliar with coherence measurements, is essentially a quality measure where values close to 0 represent low quality data that doesn't have a very high signal to noise ratio. And on the other side, you have high coherence data, typically near values of 1, that provide very, very reliable results. And then built on top of that, there's also a reliability mask. If you just want a kind of a binary yes, no, which of these pixel measurements of displacement are reliable from the opera team's perspective, this reliability mask will be 1 in locations where they believe the data is reliable and 0 where it is not. And this is kind of a nice feature if you just want to quickly filter out to, okay, what's the highest quality data versus the lower quality data. And so that covers just some of the basics of the OPERA displacement data set. And I'd encourage you to go to the OPERA displacement page and view their product guide if you want to dive a little bit deeper into that. And I can certainly talk about some of that in the QA session as well. But I also just wanted to mention a few caveats right off the bat in case people are unfamiliar working with InSAR data. And the first caveat I want to mention right off the bat is that the displacement that's measured in these products is displacement along the satellite's line of sight, or basically along the line that the beam that we were talking about earlier travels from the satellite down to the ground and back up. And this is really important because typically star satellites look off to the side, and this means that there is both a horizontal and a vertical component of the displacement measurement being made. And this can be a little confusing for people who are working with it for the first time, because you might assume that the displacement measured is vertical and that's what you might be expecting, but it's a little bit muddied in this case. And so just always remember that you're viewing the displacement in these products along the satellite's line of sight. And that's a value that's recorded in the metadata, and we have some helpful charts within the displacement portal to help remind you of this fact. Now, another really important thing to mention is that all satellites kind of have or all polar orbiting satellites have kind of an ascending track and a descending track, which they'll typically get data for a given location, both on this ascending track and on the descending track. And the important thing here to remember is that basically for a given location, there will be 2 very different line of sights of data available for this InSAR data set. And so just make sure when you're working with these displacement data sets that you're keeping track of, okay, am I using ascending data in this case or descending data in this case? And in particular, if you're kind of new to working with this type of data, I recommend at first you stick with either just ascending or just descending data and work with them separately. There are ways to combine them to get at a better measure of truly vertical displacement, but I won't get into that today. Along with this line of sight caveat, another good thing to remember is that the displacement in these products is always being measured between a specified reference and secondary date. And these reference and secondary dates are recorded directly in the file names as well as in the metadata of the files themselves. And so what do I mean about displacement being between a reference and a secondary date? So the important thing to remember here is that if you're looking at the displacement in an OPERA-DISP granule, it is recording the displacement between some date 1 and some later date, call it date 2. And while the secondary date changes with every granule, sometimes the reference date will stay the same for a period of time. So here on this graph, we have product number, which basically represents a series of OPERA displacement products for the same locations. And here on the x-axis, we have different dates, date 1, date 2, date 3, date 4, etc. Now, the way that the OPERA displacement data sets are created is that the first product, called product number 1, is going to measure the displacement between date 1 and date 2. And then the next product won't change its reference date, but it will change its secondary data set. So now the data or the displacement measured will be between date 1 and date 3. And you'll notice that the displacement between date 1 and date 2 is in some way also recorded in date 2, in product number 2, because it's also spanning that date 1 to date 2 timeframe plus a little bit more. And then, this goes on with product number 3. It's now measuring displacement between date 1 and date 4. And then with product number 4, it'll go from date 1 to date 5. Now, an important thing to remember is that while the OPERA displacement data set will maintain a reference date for a small stack, and this is typically on the order of 15 products or so, at a certain point, they will also change the reference date. So it'll stay static for here, it's 4 products, but in the actual OPERA-DISP archive, I believe it's around 15. But at that point, now the secondary date from the previous product will become the new reference date. And so the next product, product number 5, will have a reference date of date 5, and then a secondary date of date 6, and then this pattern will continue until we switch reference dates again. Now, the important thing to remember here is that you need to be keeping track of this and accounting for this if you work with the data yourself. And this is important because if you basically don't add the displacement recorded for date 1 through date 5 in this product number 4 to these granules up here, you won't be measuring the displacement for the whole time period. If you want to recover the displacement from date 1 to date 6, you need to add product number 4 to product number 5. Now, this is a detail that we have worked out for you inside of our displacement portal. But if you're working with these products yourself, just be aware of that, because this could be a potential stumbling block. So now that we've gone through some caveats and some basics of what these products are, I want to talk to you about the ASF Displacement Portal. As you may have gathered from what I've said so far, while this is a very powerful and informative data set, it can be a little challenging to work with at times. And in particular, it can be challenging if you want to look at very large areas or reconstruct the time series for a very long period of time. And so to help with this, we've created a new portal kind of built on the back of Vertex called the ASF Displacement Portal, which is an open source web interface for working with the OPERA-DISP dataset. It both offers a very large overview of how displacement is occurring across the entire dataset, and then it also gives you the capability to interactively query the dataset so that you can look at the time series in particular places with great detail. And just an important caveat here to mention is that we are using the local displacement in the ASF displacement portal. So just be aware that the signal you're seeing is related to this local displacement layer within the products and not the standard displacement layer. So that's been a lot of slides, but the thing I would actually really like to show you all today is a quick demo of this displacement portal. Okay, so let me get out of the big view here and hop over to the displacement portal. So for those of you who want to follow along, you can find the displacement portal at displacement.asf.alaska.edu. And when you go to there, the first thing you're greeted with is just an overview of the measured velocity computed from the time series of displacement values for all of the OPERA-DISP archive that we have here at ASF as it currently stands. In this in this map, blue values represent movement away from the satellite, or basically motion with a more downward component, and then red values represent motion towards the satellite, which is a mostly upward component to it. And you have many controls here, just like you'd imagine with a standard Slippy map. You can grab the map and pan around. You can zoom in with your scroll wheel. And then we have some options over here on the left that allow you to do a couple of things. First, you can toggle on and off this velocity map. And then in addition, you can change the opacity of the map. So this is great if you want to take a peek at what is the underlying imagery below it, or if you want to see just the velocity values derived from the displacement information, you can set the opacity to 100% here. Now, another couple of things to notice, first of all, is that you'll see here that we have your flight direction. And this is going back to the ascending versus descending orbit that I was talking about earlier. You can flip this back and forth. So we can go from the ascending view to the descending view, and you'll see that the underlying maps update. And now you're seeing the velocity as recorded by the OPERA-DISP dataset using the descending flight direction. In addition, next to the flight direction controls, we also have little graphics that describe a little bit about what the geometry of the satellite line of sight is in that given flight direction. So here we're seeing that the radar look direction is roughly 283 degrees, and that our incidence angle, depending on where you are in the swaths of the image, is between 29 and 46 degrees. Over here on the right-hand side, you have a couple options that I'll get into a little bit later for sharing what you've looked at. On this info button, it'll actually take you to a link with more information about these products where you can start to learn more about them. You can look at technical guides and information as well. And then one thing we're very excited about as well is that this OPERA Displacement Portal also fully supports the Spanish language. So you can flip over to Espanol here, and the vast majority of the portal, with the exception of some very technical language, will change over to the Spanish language. And then as well, over here, we have documentation about the individual layers as well. If you click on the one next to the velocity layer, it'll go into some information about how we actually calculate this velocity layer using the OPERA displacement products. And then along with the velocity layer, we also provide a rollout layer. And this just provides a broad overview of how the data for OPERA-DISP will be back populated through time. So as you'll see, the data that we currently have in the archive roughly matches the first phase of the rollout, and the OPERA team will be continued to create these products for phase one. And then once they're done with phase two, they'll move on, or sorry, once they're done with phase one, they'll move on to phase two, which is going to be mostly Central America and the southeastern US. And then after that, they'll move on to some of the more northern US from there. Okay, so this is kind of the broad overview, and this is kind of one half of what's great about the portal. And the other thing that we're really excited about that actually took a lot of engineering work behind the scenes, and I'd be happy to talk a little bit more about how we're doing this if people are interested, but we've also created the capability to actually spatially query this data to look at the time series of displacement. And how this actually works is you can zoom in on a particular area of interest. Say I'm somebody who's very interested in looking for groundwater withdrawal. I've zoomed and panned around, and I see an area that looks particularly interesting to me and looks a little suspicious. For me, I'm particularly thinking about groundwater. There could be groundwater withdrawal in this location because first, underneath the image, I'm seeing some agricultural regions that have they're clearly using some center pivot irrigation. So I know that there is some agriculture in this region. And then also, if I increase the opacity here, you can see a very strong blue color on the map, which means movement away from the satellite and in general, depression of the ground, which is the type of signal we would expect for groundwater withdrawal as well. So, okay, I found this area I'm really interested in. And now using my mouse, I can point and click on a particular location, and behind the scenes, ASF is going through parsing all of the OPERA-DISP granules that we have for that location in our archive and returning to you a time series of the deformation of that location. So just to walk you through what you're seeing here in this graph, first over here on the left-hand side, you have the name of the series you clicked on and a little check mark. You can click the series on and off using this check mark. And then if you ever wanted to delete a series for any reason, you can also use that trash can button right there. Now, in the main portion of the map, we have a couple things. First, on the y-axis here, we have the local displacement as it's measured in meters. And then the x-axis here is just time, beginning in mid-2016, where the OPERA-DISP granules start for this location, and extending all the way through mid-2024 as well. And then a couple other controls here is that you can actually control what date or time you're looking at by changing these time slider bars on the bottom. And then, as well as changing these time slider bars as well, you can actually interactively zoom and pan in on this map as well by pointing and clicking on the map or using your scroll wheel to zoom in on particular locations. And this is really nice if there's a particular time period you're interested in as well. And then a couple of things just looking at this that I always find really interesting in location is that you can see one of these temporal patterns that I was talking about earlier, which is that you can see through the like annual cycles, a period where you see kind of a slight uplift and then a slight subsidence over and over again. And this is another indication that the displacement recorded in this area might be related to groundwater withdrawal, because it's following that type of annual cycle that we would expect for irrigation. Now, along with just being able to look at the data, you can mouse over specific points and you can get the specific values associated with that. That'll be the date and then the specific displacement measurement that was recorded for that date. And then over here at this little gearbox, you also have some additional options. The first is you can show lines to just connect these dots together. This can be kind of nice for just understanding which time series goes with other time series, which starts to be really useful. Say if I click on a few more points here and load them in, you'll see that it can start to get a little crowded, and sometimes the lines have you kind of track one particular time series over and over again. And then once again, another thing that's good to mention now that we have multiple series up here is that if you mouse over a particular series on the left-hand side, you'll see that it's both highlighted in the graph here. And then if you look up in the actual map area, you'll see a red circle around the series that I have highlighted over on the left. So that just helps you kind of keep track of, okay, I've clicked on a bunch of series, which one am I actively looking at right now? And then in addition to that show lines feature, we also have the ability to show linear fit. Now this can be really great if you just want a quick estimate of what the velocity is for a particular series that you're looking at. And here we can look at the slope component of this linear fit and see that, okay, in here, we're seeing an average velocity of about 1 centimeter of movement per year. So already this is a lot more than we offered at any other data set at ASF. You know, we're really excited about bringing these really interactive capabilities to this data set. And then one more thing to mention is that, okay, you've done this analysis, it's great. You might be trying to figure out, okay, so how do I save what I've done? The first thing that you can do here is go to export, and you can export the data that you're seeing in the graph here as a CSV. You can download it and create your own graphs or your own analyses with it. But then also, one of the great things that we have on this website is static linking. So basically you can see that the URL up here is very long, and that's because the entire state of the displacement portal as it is currently being shown to you is recorded in this URL. So if I click on it and copy and paste and either send it to a colleague or save it somewhere for myself to look at later, what you'll see is that if you put that URL in, you'll be fully able to recover the exact state that the portal is in when you looked at it. And then in addition, if you go over here to share, you can then share this link either by email or you can just copy it directly to your clipboard like that. So that's the ASF Displacement Portal. We're really excited about it. You know, we're just getting started in this field, and we're really excited to have you guys try it out, see what works, see what doesn't, and yeah, just have fun exploring these OPERA-DISP products. I've had a chance to look at these products while we've been building this thing, and I've been really impressed by them. And I think anybody using time series InSAR data in their own analysis is going to be really impressed by these products and going to get a lot of use out of them. So at this point, I'm going to flip back to the presentation and just mention a few things. So throughout this talk, I've mentioned a few different websites that you all might want to go look at. The first is if you want to go look at this displacement portal and try it for yourself today, you can just go to displacement.asf.alaska.edu and start using it today. If you want to learn more about these products, probably the best place to go is this JPL address right here. That's jpl.nasa.gov/go/opera/products/DISP product suite. This is where you'll find that product description document I was talking about, as well as some broader information about the OPERA project. They have a lot of other great products that we also host at ASF that are also coming out of here. The OPERA RTCs are one we've been hosting for a while now. And so you might also be interested to learn about their other products. And then the third link that I also wanted to mention, which is just our Vertex site, which is search.asf.alaska.edu. If you want to download the actual granules that back up this displacement portal, or if you would like to download other SAR data sets from NASA, this is the best place to go. Yeah, give it a try. I'm imagining some of you are already familiar with Vertex, but if you're very new to this space, if you want your SAR data, this is the best place to go. So I think with that, I will end my talk. I just wanted to mention, if you have more detailed questions that you want to ask for ASF about this portal and what you can do with it, I'd recommend you contact uso@asf.alaska.edu. This is kind of our help and customer service email. And yeah, try out the portal today, and I'd be very excited to answer any questions that you all have.
All right. Well, thank you so much, Forrest. At this point, I have opened up the final end polls, the optional polls. We really appreciate your feedback on that. But since we have quite a few questions, let's go ahead and dive in. I have a question, and bear with me if there's a question that has already been responded to with a text response, but perhaps a little bit further down from the question. So the first question is, if 20 buildings exist within a 5 by 20 meter pixel cell, can we obtain displacement? Excuse me, I gotta close the chat here so that it's like obscuring my view. All right. If 20 buildings exist within a 5 by 20 meter pixel cell, can we obtain displacement measurements for all 20 buildings, PS points, using the PS InSAR technique?
So in this context, you are going to be roughly limited by the resolution of the SAR data that you're working with. If the pixels themselves are 5 by 20 meters, which is close to what the Sentinel-1 data is, and you have multiple buildings within that, the scattering signal of the amplitude and phase component that I discussed earlier is going to be a combination of all of the interactions that occurred within those buildings and then was reflected back. So I don't believe you're going to be able to discriminate between specific buildings within a pixel, unfortunately. Now, if you're really interested and need that finer grain detail, there are, for purchase, some higher resolution SAR data sets that you can get. A couple companies are ISI, Umbra, and Capella come to mind. But yeah, unfortunately, you're roughly limited by the pixel size, and your best option is to try and buy commercial data, although unfortunately that can be quite expensive.
Okay, and thank you so much, Forrest. I do want to say one thing. There are some commercial data sets that are available if you meet the requirements for the EULA through NASA's Commercial Satellite Data Acquisition Program. I can put a link in the chat later. The next question is DS processing the same as PS? And then just for our Q&A panelists, please feel free to unmute, if one of you wants to take the questions. I defer to the ASF team to determine that.
No, the techniques are slightly different, mainly to account for the extra averaging that occurs within DS processing. In particular, the most common type of DS processing that most people are familiar with is the SBAS, or small baseline subset processing technique. And the key difference between PS plus DS processing goes back to the stability of the signal. So one thing I didn't cover, unfortunately, is that For distributed scatterers, because they're in general a little less coherent and less stable through time, there comes a certain length of time over which they stop being coherent. So you could imagine something like after 2 months separating the two images that you're using to create your InSAR pair, you're no longer able to have a high enough signal to noise ratio to get high quality data. And so what typically happens with DS analyses, they use a small baseline, which is another way to say like a short time window subset of all of the possible interferogram or InSAR combinations you could do. On the DS side, because those pixels or those features remain so much more stable, they maintain coherence for much longer periods of time. And so you can actually create a usable InSAR image for a PS scatterer when the when the two images are taken more than a year apart. And so you use many, many more combinations, and sometimes in some PS workloads, you actually use all possible combinations of images together to create the network of interferograms that actually go into creating your time series InSAR solution. So that's kind of the key difference between PS and DS. And when you combine both those together, you just use generally smaller subsets on the DS side, but then use those longer subsets for the PS side.
Okay, thank you. And okay here. All right, so the next question is, first, the participant is thanking you for the presentation. And the question is regarding the use of distributed scatterers. In my experience working in vegetated regions for geohazard applications, DS targets often exhibit increased noise levels and reduced coherence, particularly over small or local scale study areas. Consequently, the overall quality of DS appears to be lower compared to persistent scatterers. Given these limitations, would it be methodologically sound to integrate both PS and DS in a single analysis?
Yep, yeah, and that's exactly what the OPERA displacement products are doing, is that they combine both of these techniques together. When you have high enough data quality to actually do PS, that's what they're doing. And then as the quality starts to drop off, they use a more of a DS method to perform it. Now, one thing that is important to mention, since they brought up vegetation and things like that, is that the overall quality and the signal to noise ratio, that you get for InSAR data is heavily dependent upon the sensor and also the particular wavelength that you're observing for SAR. Now, SAR satellites come in a variety of different wavelengths or bands, is the term typically used in the field. And Sentinel-1 is that C-band, which is typically pretty good for monitoring things like grasslands or tilled areas or agricultural fields, but it can have a real tough time actually making measurements of like forested areas or things with very large and dense vegetation. However, due to how different wavelengths interact with the Earth's surface, L-band SAR data, which is what the new NISAR mission that is going to be launched later this year is going to be using, and I believe there are plans to also create OPERA-DISP datasets using NISAR data. They are much less affected by vegetation. And so I'd encourage the person asking the question to give NISAR a try in a couple of months and see if they can get better results using the L-band NISAR data, and maybe those areas that you couldn't get very high quality with the DS for Sentinel-1 data, you might be able to with NISAR data.
Okay, well, thank you again, Forrest. The next question is, from two images, how much realistic change can we measure? Let's say one image from January and another image from December. Subsidence happened, how much can be measured? And for the same study, 12 images each month, how will the results come?
Okay, so I'll try and answer that question. The key thing to remember is that you are measuring changes in phase when you're performing InSAR. And an important thing to remember is that if the change in the distance between the satellite and the ground is large enough that you go more than a phase cycle, so you go through a peak, through a trough, and then back again, it starts to become very ambiguous how far you've actually gone. And there are some advanced techniques in the unwrapping space, which I can talk about if people are interested in, that can maybe help you start to recover some displacement that is larger than a phase cycle. But in general, you are limited by measuring deformation that increases the path length less than a phase cycle. And an important thing to remember there is that because the signal has to go down to the ground surface and then back up, a movement of the Earth of half of the phase cycle will actually increase the path length by a full phase cycle, because you have to go down and back. So for a roughly 5 centimeter wavelength like Sentinel-1 has, that means that in a single image, you typically can't measure deformation or displacement larger than 2.5 centimeters. Now, once again, this will be very different when we have NISAR. It's going to be operating at much closer to a 24 centimeter wavelength. And so you'll actually be able to measure displacement in single images on the order of up to like 12 centimeters instead.
Okay, well, that's excellent. I appreciate this. The next question is for us. There are only 2 images, 12 days temporal baseline. Can you measure 5 millimeters difference?
Yes, you likely can with Sentinel-1. 5 millimeters is pretty small, so you might have other sources of noise in the data at that level that might be hard to identify a true 5 millimeter signal, but this is where something like time series InSAR can help out. It's very common that the type of displacement that people are interested in monitoring, such as landslides or groundwater withdrawal, tend to occur consistently over time. And so when you integrate data from multiple time series, the random noise can average out a little bit, and you'll see actual displacement signals be amplified a little bit. And so that's one of the other really important reasons why time series InSAR is a really great technique. It really improves the signal to noise ratio of the InSAR data overall.
All right, moving on to the next 2 questions. First, time series InSAR measurements might be affected by climatic factors, for example, precipitation, even in urban areas. Surfaces like agricultural fields or bare land are especially sensitive. How do you account for these environmental effects? That's part 1. Part 2 is, why is the spatial resolution 30 meters? Sentinel-1 provides data at 10 meters, doesn't it? And if you need me to repeat any of that, let me know.
Yeah, I'll take the second half of that first. So once again, this all comes back to creating a data set that is high enough quality that we feel that the Opera team feels confident sharing with people. And when you start working at a very individual pixel by pixel level, the ratio of signal to noise in the data is actually not what we would really like it to be. And you would see the same thing if you worked with optical data. It's hard to get really good measurements of some sort of reflectness on a single pixel basis, although there are some extra factors that make this challenging with SAR data. In particular, I'm talking about speckle. So we increase the resolution just a little bit, we decrease the resolution just a little bit. We use slightly larger pixel measurements so that we can overall create a better product. And while you could theoretically produce a product at a slightly higher resolution, it's likely that the actual information and usable content there would be about the same, but there would just be more noise in it. So 30 meters tends to be about the best place to end up. And you'll see some people even go farther than this. A lot of Sentinel-1 time series InSAR analyses will actually do their analyses at something maybe even closer to 40 to 100 meter pixel sizes. So in general, actually, OPERA-DISP is kind of on the lower end for Sentinel-1 analyses. And then Going into environmental effects, yes. In particular, one thing that we worry a lot about with InSAR data is changes to, particularly for Sun1, is changes to the amount of water in the atmosphere, particularly in the tropospheric layer, and changes in the water content of that layer can actually slightly change the refractive index of the atmosphere, which can increase the path length that it takes for the signal to go from the satellite down to the ground and back. And typically what is done to help correct for this is to actually use external weather models to make a prediction of, okay, given the state of the troposphere at this location on this day, what is the expected delay that we would expect for the SAR signal we've measured? And this is actually something that the OPERA displacement team has, or the OPERA team has been working on. I don't believe it's directly in the products, but they are creating a correction layer that we're also going to host at ASF that will provide a tropospheric correction to remove some of those effects of the wet versus dry atmosphere conditions. And then to kind of the third point there, yeah, it can be a challenge when different moisture content on the actual surface either changes the reflective properties for the SAR signal or actually causes some shrink swell in the ground itself. And so the best recommendation there is to actually use time series InSAR. You can get rid of a lot of these small temporal window effects, such as like, was it rainy or not rainy on a given day, if you're just integrating data from many, many dates together.
Okay, I do want to say, because we have a lot of questions, a few have been responded to with a text response. So if we do not get to your question in the next 15 minutes or let's see, 18 minutes, our speaker and the Q&A panelists will be able to get in touch with you offline. I'm going to send them the Q&A log, and so we can follow up, okay? So the next question is there a way to reproduce this data set for South America? If so, how?
So yeah, unfortunately, I forgot to mention this, but the OPERA team has done a really fantastic job of actually fully releasing the code they use to produce these products fully open source. And so if you go to their GitHub page, let me actually bring up get you the specific URL here. I believe it's github.com/opera-adt/compass. Yeah, or no, not compass. Dolphin, I think is the name of it. And I apologize, I'm not sure what the best way for me to get this into.
You could just place it in the chat if you'd like to. And then,
Sure.
the other thing, Forrest, I can include a link to, information about the links that have been shared when I follow up with users so that they have a record of it as well, okay? Okay, so the next question is, which incidence angle is more suitable for PS InSAR in your point of view?
Both ascending and descending data are roughly the same. I wouldn't prefer one over the other. The only thing to think about is that if you're in urban environments where things are strongly oriented along one particular direction, so I'm thinking about city blocks that head in a particular direction, the typical thing you want is for the broad side of the buildings, the very flat exposed side. You want that to be roughly pointing towards the satellite line of sight so that you get a nice big surface for something to bounce off of. But I don't think you're going to find a massive difference overall. I think using both ascending and descending will be fine.
Okay, thank you. So the next question is are there some methods that solved the 3D displacements by InSAR?
So yeah, this is something that the OPERA team is actually working very hard on. I don't know about the timeline here, but they're working very hard to produce a vertical land motion product, which will basically integrate the information from both the ascending and the descending paths, and get you a calibrated measurement of what the vertical motion is in a particular location. And they might have just released a paper about this. So let me see if I can find that link for you all real quick.
All right. Would you like me to wait for the next question while you're looking that up, or shall I continue forward?
Shoot, I might not be able to find it right away. That might be something I need to follow up on. So let's move on to the next question.
Okay, so the next question is the reliability mask solely based on coherence values? Excuse me. If it is, how do you determine the threshold for the classification? If not, what else do you consider when creating the reliability mask?
Yeah, I might have to apologize to the question asker here. I don't want to get the details wrong in this context, and I can't remember off the top of my head what the exact calculation is to get to that reliability mask. In particular, because I'm on the ASF side and I wasn't as involved in the actual creation of the algorithm. So the best thing that I can do is that the OPERA team is working very hard right now to actually create a document summarizing all of the algorithm and basically all the algorithmic choices they made and how every product is being created. And as soon as they release that document, we can make sure it's discoverable for you all to look at. But I believe there might be more than just coherence going into the creation of that, into the creation of that reliability mask.
All right, well, thank you, Forrest. And again, I'm happy to include these links in the follow-up message to both registrants and participants once we have these links together. Moving on to the next question, we are now in the extended Q&A period. What is the time frame for that we can download? I need historical displacement data from 2003.
So the Sentinel-1 mission did not start until 2015, and there were some really important data quality changes in mid-2016 that make it can make it more challenging to do these types of analyses with Sentinel-1 data before that time. So this data set starts in mid-2016, and unfortunately, that's about the earliest we're going to be able to go. There are older satellites, but that data can be a little more challenging to find and download. In general, though, ALOS 2 might be one of your better bets if you're looking for data from that time period.
Okay, well, thank you, Forrest. And the next question is, please explain the use of this tool if I'm going to, find out the displacement in north-south, east-west, and up-down direction.
Yeah, so once again, this is something that there are some pretty good papers on how you do this. It's called a decomposition, where basically you integrate the information on, okay, here's the ascending pass and the descending pass, and from that, let's derive a vertical motion and then a horizontal motion. Now, unfortunately, because you only have two discrete look directions, the ascending and the descending pass for a particular location, you aren't able to fully resolve north-south for Sentinel-1 SAR data. You can only resolve the vertical component and the east-west component. But this is something that the team is working on, and we can probably scrounge up a paper to include in the links that describes how you do that decomposition.
All right, thank you. The next question is, we know that InSAR technique is relative, and I would like to know, what about the reference? I don't know if this is intended to say reference point. Do you just have one reference point for the whole area, or is it a network of reference points maybe?
So yes, this is another caveat that's good to mention, is that the individual, like as the question asker said, InSAR measurements are always relative to a particular location within the image. And in particular, you'll want to keep track of, if you're working with this displacement data yourself, you'll need to keep track of where that reference point is, because I do believe it can change from granule to granule. This is something that we've dealt with in the ASF Displacement Portal for you, and in particular, it is not as relevant for the local displacement because you're basically doing a local average filter, so you're only looking at very local motion. So the type of motion that would change based on the reference point really isn't present in the local displacement layer anymore. But this is another big thing that the team is trying to tackle. Another big thing the team is trying to tackle with their vertical land motion products. I believe the idea is that it's going to be a fully calibrated product that is going to be referenced to GPS and GNS surveyed locations.
Okay, thank you. The next question is actually one for me. Asking about where you can find information about products and upcoming webinar trainings. So I think the Earth Data's website might be down at the current moment, but to learn about data products, you can go to earthdata.nasa.gov. That should be back up shortly. And for upcoming webinar trainings, when we are finished, I will post a listserv subscription email address in the chat that you can use to subscribe for upcoming webinar announcements from our project. All right, so with that, I'm going to move on to the next question. Is there, making sure, been trying to check to make sure if, okay, looks like Greg answered this one. Okay, bear with me for a moment if you would, thank you. Okay, what causes the fluctuations in the time series deformation curve? Could these variations be attributed to factors like atmospheric conditions, sensor noise, or other external influences?
Yeah, basically the temporal changes will vary a lot on what you're looking at, and there is certainly a degree of noise related to the features that the question asker was talking about. But there are typically like wet and dry cycles for a particular location are one reason why you might see like these annual temporal cycles for the data. My research background particularly comes from time series InSAR for landslide motion. And that's something where you see a very strong annual cycle based on what the water content is at a particular time. But the reasons why you might see temporal changes in the displacement are as varied as the reasons why you might see displacement. It really depends on what you're looking at, and really an important part of the science that you are all doing is figuring out, okay, I'm seeing this signal in the displacement data or these patterns. Can I attribute this to particular physical phenomenon, or might this just be a noise issue?
I really appreciate the Q&A panelists' input in the chat, and also Forrest, all of your expertise here. So thank you. And let me move on to the next question. The next question is, what is the accuracy level for the results?
So I apologize, I don't know that offhand. I know that calibration validation exercise was gone through, and I believe that that information can be found in the products, but that's something we can follow up on.
Absolutely. The next question is, and again, I will send all of you the Q&A log in the chat, so you'll be able to do that. Okay, so the next question is, just making sure someone not responded to it. Okay, the product covers some agricultural regions, but neighboring fields were missing. How should this be interpreted? Is the product accurate for agricultural areas where land cover changes due to vegetation growth may be more significant than actual displacement?
Yes, this brings an important point. So for the ASF Displacement Portal,
oh, I do actually see that Greg also provided a response, but go ahead here.
Yeah, I think this is worth mentioning to the broader group, which is that in the portal, we actually do mask out in the map using the reliability mask that the OPERA team has provided in these products. So for areas that are consistently unreliable, you're not going to see data in the map. However, there is still data at that location, and if you use the Explorer capability to actually click on a series within that location, you will see what data is available for that location. So you can still use the products in those locations, but with the caveats that you should be careful. You know, when you imagine if you had a cornfield or something, if you have corn that throughout a cycle is growing from basically 0 meters to 2 meters over the course of a summer, you know, that is a type of movement that is likely too fast for InSAR to capture. So you're going to see not very coherent data. So yeah, just be careful with that.
All right, wonderful, thank you. So the next question is, some points are solid, others are hollow and dotted outline. Can you confirm the dotted outline points are just continuations of the last known point?
Yes, that is another good related point, which is that the way that we denote lower quality data, basically data that didn't pass the reliability threshold available in the reliability mask in that time series data section, is that we make those hollow circles with dotted lines. And so this is just a note to you, like, hey, like there may be information at this location, but it's not overly reliable. And in general, the assumption that we've made in creating those charts is that we're just assuming if we don't have reliable data, that we're going to assume that no displacement has occurred. Now that could be wrong, that could be right, but with the information available to us, that's the best we can do.
Okay, thank you, Forrest. I think the next question has been touched upon, but I'm going to read it just in case. And if we've already covered it, you feel adequately, then we can move on to the next. So you have the loss velocity for both ASC and DSC orbit. Any chance to get the vertical horizontal velocity for these data sets? And I believe you were saying that the team is working on the development for these products.
Yep, the team is working on creating that vertical product, and then I think in the Q&A summary, we'll also send a paper just describing how you would do the decomposition yourself if people are interested in it.
And so, since there are quite a few questions on the topic of coverage, spatial coverage, I'm just kind of going to group it together, group some of them together, because some folks are asking if in the future, if it will be possible to obtain results or data for worldwide regions.
You know, I think that is something that the OPERA team and us would be ecstatic to provide. It just comes down to a question of funding. With the funding available at the given time, you know, we were able to do North America, but I imagine, you know, if there are broader NASA surveys where scientists are asked, what data would you like to see in this future? And there's a very large cohort of people who say, we want the OPERA-DISP globally. I think that's something they might be responsive to.
Excellent. Okay. So the next question is, we probably have time possibly for one more after this. Do you have a rough timeline for when phase 2 and phase 3 will be ready? Additionally, is there a plan for, well, we covered the second part. So let's leave it with, do you have a rough timeline for when phase 2 and phase 3 will be ready?
Yeah, it's going to be very rough. I think it really depends on how things go, but I would say that phase 1 is probably going to take through the maybe the end of this year, and then maybe early next year, phase 2, and then maybe quarter 2, quarter 3, you might be seeing phase 3. But that's all kind of in flux and will be probably changing from time to time. And probably the best way to know where we're at is to just check back on the portal. You know, we're updating the portal weekly as the new data comes in. So you should be able to know if there's coverage in an area you're interested in by checking out the portal.
All right, and we have reached our maximum time for questions. So what will happen now is I will leave the virtual meeting space opened for an additional 10 minutes or so if our Q&A panelists and our speaker want to stick around and try to provide text responses to some of these questions, that's great. If not, there's no obligation to do so. As I said, I will forward the Q&A log in the chat to both our Q&A panelists and our speaker for this afternoon, and they will be able to follow up with you offline. So at this point, I'd like to thank our speaker for this afternoon, Forrest Williams, and also my backup host, Geraldine Tuart and Joseph Smith, and then the Q&A panelists from ASF, Gregory Short and Kathleen Christensen. We really appreciate all of you, and really, we appreciate our webinar participants. So thank you so much for the very thoughtful polling question responses, and also for your questions today. There's tremendous interest in this product, and we hope that we will see you at an upcoming webinar event. So with that, we'll log off from the audio component, and I'll leave the virtual meeting space open an additional 10 minutes.
And I do apologize. I do have another meeting I need to get to here.
That's okay. Thanks, everybody. Take care now. All right. Goodbye.
Thank you all for attending.